Bon, je pense qu'on va pouvoir commencer. Donc aujourd'hui, on a le plaisir d'accueillir Rebeca Ribeiro-Palau qui va nous parler de matériaux moirés, avec surtout un point de vue expérimental. Rebeca est originaire du Venezuela, où elle a fait la première partie de ses études. Puis elle a fait une thèse en France, à l'Université Paul Sabatier, je crois, à Toulouse. Ensuite, un premier postdoc en métrologie. Et puis un second postdoc à l'Université Columbia, en particulier dans le groupe de Corridine, où il a fait des très jolies choses sur les matériaux moirés et la possibilité de contrôler l'angle de twist dans ces matériaux. Et donc aujourd'hui, elle est maintenant chercheuse CNRS au C2N sur le plateau de Saclay, où elle montre son activité expérimentale sur ce sujet. Et elle va nous parler donc d'état topologique dans les matériaux de moiré, en particulier du point de vue d'une expérimentatrice.
Thank you very much. So, thanks for coming, even if we have a heat wave outside. You made the trip, so thank you very much. So today we are gonna see all what is the topological states that we found nowadays in Moiré materials. I'm gonna focalize especially in graphene-based materials. First, to keep just track of all the evolution in graphene, and second, because last week Nicolas Regnault gave an excellent introduction to the topological states that we already see in TMDs, in twisted TMDs materials. So this talk, if you read the abstract, is going to go in the following way. We are going to start introducing the quantum Hall effect and fractional quantum Hall effect into the materials and Moiré materials, and then we're going to jump into newer things as the anomalous quantum Hall effect into the materials. So to be completely honest, this is a little bit ambitious abstract or outline. So I'm going to skip part of the fractional quantum Hall effect, because also next week you are going to have a talk by Wendell Febvre, who is going to cover most of it, at least in 2D electron gases. So the objectives of this seminar, what I want you to have a look during this talk, or to understand at the end of the talk, is first the experimental observations and phenomenology of the quantum Hall effect, which comes a little bit to complete Antoine's course of all the theory about it. Then the modifications of this of the quantum Hall effect when we have a Moiré superlattice, and how this gives rise to anomalous quantum Hall effect. And at the end of this talk, what is important to discuss is whether we need a Moiré superlattice or not to observe all these effects, okay? So I think it's a little bit unorthodox here, but if you have a question, a quick question, something that you need to understand in order to continue, please just interrupt me, okay? If I think it's a very, very long answer, I'm gonna just tell you that we can discuss later, okay? But don't worry, just interrupt me. So for me, there is no way to talk about topological states, at least in an experimental point of view, that do not start talking about the first observation of the integer quantum Hall effect in the 80s by von Klitzing. So here you can see the first measurement was performed in silicon MOSFETs at quite high magnetic field and low temperatures. And the main characteristics of these experimental measurements are that when you are in some gate value, so let's say for example here, your longitudinal resistance drops to 0 and your Hall resistance is quantized, and it's perfectly quantized in terms of fundamental constants of nature. So how can we see this? Well, there are two ways. Antoine just said this before. When you have a two-dimensional electron gas and you apply a magnetic field, you can describe this as classical orbits of, by the Lorentz force, where your electrons are going to start to describe these orbits that are going to be localized. And you can see this quantum mechanically as the formation of Landau levels. So these Landau levels are going to have localized electrons in space and are going to be highly degenerate. Okay? So now, the materials where we observe quantum Hall effect are many, but the most stable, or the ones that are most studied so far, is two-dimensional electron gases made of gallium arsenide, aluminium gallium arsenide. And these are constructed by the fact that when you have two semiconductors that with a different energy gap, you're going to have a band bending, and at the interface of this band bending, you're going to have a conduction, a two-dimensional conduction of electrons, which is called a two-dimensional electron gas. These are made in molecular beam epitaxy machines, which are these huge machines with extremely high and demanding performing conditions, where you need to be very, very clean and have extreme vacuum. So just to show you how an MBE works, I'm going to show you this example. This is a gallium arsenide nanowire. First, you're going to look here, okay, aside. So you can see now that every layer of atoms is deposited one by one, okay? So this allows you to have a very good crystallinity, and this allows you to have a very high mobilities, which are necessary for these heterostructures, these conventional two-dimensional electron gases. So in a two-dimensional electron gas like gallium arsenide, we have a parabolic energy dispersion. These are, in fact, momentum and energy resolved tunneling spectroscopy, because unfortunately in gallium arsenide, as this is a buried structure, we cannot perform ARPES as the ones that Antoine showed before. So you can see that we have a parabolic energy dispersion, and as we apply the magnetic field, we're going to see that this energy dispersion splits in Landau levels. And as you increase and increase, the splitting between Landau levels becomes larger and larger, okay? And that, of course, is going to have consequence in what we are interested most, the quantum Hall effect, okay? So let's say that we have the same two-dimensional electron gas with a magnetic field applied out of plane, and we're going to measure two quantities. We are going to measure the longitudinal voltage or resistance and the Hall voltage on resistance. So you need to remember that now you have Landau levels that are equally spaced in this case. So when we measure the resistance, the longitudinal resistance, what we are going to see is an oscillation, a very fast oscillation at low magnetic field, and then eventually becomes slower, and in between two oscillations, this longitudinal resistance drops to zero. At the same time, the transverse resistance is going to describe plateaus, and these plateaus are going to be quantized, okay, in terms of fundamental constants of nature. And this is so well quantized that, in fact, this value is the practical electrical resistance standard of the International System of Units since the 90s. Okay, so now, but why is like this? So we saw the bulk edge correspondence just before, and to explain this, we're going to have the Landau level formation that I told you before, and now we're going to see how this energy changes as a function of the position in the material. So as Antoine said before, we're going to have two different topological orders. Outside the sample, you're going to have a zero Chaire number, for example, and inside you're going to have a, let's say, Chaire number of 2, which means that your Fermi energy is placed between the second and third Landau level. So now, if we look what happened on the edges, because we know that gapless states must exist in the interface between two topological phases, we're going to see that we have dispersive modes. These dispersive modes are going to be the responsible of two things. The first one, the drop into zero of the longitudinal resistance, because now the conduction between this electrode and this electrode is a perfect conduction, because we cannot backscatter from this edge to the other edge of the sample. This is exactly the same as Antoine just said before. And now we are going to have a voltage drop between the two sides of the sample, which is also quantized. So, okay, this is the integer quantum Hall effect. We already know this. This is the experimental characteristic of the integer quantum Hall effect. Now, if we keep either increasing the magnetic field or making our sample cleaner, we're going to pass to a different regime, which is the fractional quantum Hall effect. So this is the original sample where the fractional quantum Hall effect was measured the first time. Doesn't look like very clean, and I'm here talking about making sample cleaner, but remember that this is a barrier structure, so it's not necessarily what you see on the surface what matters. So what happens here is that now interactions are going to be more important, and in particular interactions, your Coulomb energy is going to become more prominent or larger than both things, the thermal smearing, which means that you need to be at low temperatures, and also the Landau level broadening, or the disorder of your system. So in order to obtain a fractional quantum Hall effect, which can be seen here by the quantization of the resistance, this time in terms of the same units, the same fundamental constants, but with a filling factor or a Chaire number of 1/3, and that has exactly the same characteristics as the integer quantum Hall effect. A plateau in the Hall resistance, and at the same time a drop in the longitudinal resistance. Okay, so what is important to know, I'm not going to go into the details of the fractional quantum Hall effect, but what is important to know here is that these states shows up when your Coulomb interactions become more important than your disorder and your thermal broadening. So this was the first measurement of the fractional quantum Hall effect. Nowadays, you can see that this, well, nowadays, this is quite old paper. So there are a full zoology of fractional states, each one of them with their own interesting things. But in particular, there is one important state, or a series of very important states that are called even denominators quantum Halls, fractional quantum Hall states, that are very interesting because they are expected to have a non-abelian statistics. And this Wendell is going to cover next week. So we have integer quantum Hall effect, fractional quantum Hall effect, but if we keep cleaning our sample, if our sample starts to become even better than before, we're going to have something that is called an electron solid. Okay? This electron solid was first observed in the 90s, at the end of the 90s, by the presence of a strong anisotropy in the measurements of the longitudinal resistance and the Hall resistance as well. So you can see here that if I measure this in this configuration, where I'm applying the current like this and measure it here, this is the crystalline orientation, this arrow, okay? So the crystalline orientation of the two is going to stay the same. I'm going to change whether I measure longitudinal or in parallel to this crystalline orientation or perpendicularly to this crystalline orientation. You're going to see that especially around the even denominators, the longitudinal resistance is strongly anisotropic, okay? And the Hall resistance in both cases will go back from the fractional states that was living before to a quantized plateau of the integer quantum Hall effect, okay? So this has been associated with the formation of an electron solid, which means that the system, in order to decrease its energy, is going to arrange the electrons to form a solid. These solids can be either a bubble phase, which also includes a Wigner crystal, or a stripe phase. In this particular case, this is a stripe phase. That's why it's so anisotropic to measure in passing the current in this direction or passing the current in this direction. A more up-to-date measurement of this can be seen here. This is still gallium arsenide. You can see that now this is called a reentrant integer quantum Hall effect. It's fully quantized, and it's not just present in a very particular set of Landau level index, but contrary to that, is present in many Landau level indexes. So, okay, let's just take a second and recap. Quantum Hall effect, it's integer quantum Hall effect if you are in a single particle picture. Then if you start to increase your interactions, then you're going to have the fractional quantum Hall effect with even denominators, etc. And eventually you're going to pass to the electron solid. What does it mean? It means that if you want to study the fractional quantum Hall effect, you have a sweet spot. You cannot have a super high mobility. You cannot have the highest interaction possible, because then you're going to turn out in the electron solid. And this was pretty much the 80s and the 90s for condensed matter physicists studying these two-dimensional electron gases. Then, in the 2000s, we had graphene that showed up. You know very well that graphene is an array of hexagonal array of carbon atoms. That the most common way to obtain graphene in a lab is by the Scotch tape method, in which we just peel off layers of graphite, and of course the most common source of graphene is graphite. So now, in a practical point of view, or a more experimental point of view, if we take a layer of graphene, which, as you know, has a linear energy dispersion, and we make a device out of it, and we're going to measure transport. Okay, we are going to pass the current from this side of the device to the other side, and we're going to measure the voltage drop. As we change the Fermi energy through this gate electrode, what we are going to see is a strong increase in the resistance and then a decrease. And this peak in the resistance is the charge neutrality point, which means the point where the conduction and valence band touch each other. And this is one of the most important characteristics of graphene. We can tune the carriers from electrons to holes. Okay? So we have a knob that we didn't have in gallium arsenide. It was not as useful in gallium arsenide because you decrease the mobility of your systems. Okay? But what about the topological states? What about the quantum Hall effect? Well, now we're going to compare graphene with its linear energy dispersion to gallium arsenide with its parabolic energy dispersion. So if we apply a perpendicular magnetic field, we are not going to have the same behavior between these two. Gallium arsenide has Landau levels that are equally spaced. Graphene has Landau levels that get closer to each other. It also has the presence of an equal zero Landau level, which is a full topic of research. It has been for a long time now. And in particular, the Landau level spacing between the two first Landau levels, it's much larger in graphene. And why is this so important? Because if you take this spacing between the two Landau levels, you are going to be able to apply this new material to metrology. Okay? So in the case of when you are looking for a very highly quantized two-dimensional electron gas, the limit that you are looking for is where the energy gap is much larger than the temperature of your system. Let's say that we're going to work at 2 Kelvin. So here, for example, 200 Kelvin, it establishes a much larger gap. Okay? So in the case of gallium arsenide, as you saw before, we can measure the hole resistance. We are going to find a metrologically quantized value only within 1 Tesla at very high magnetic field, around 10 Tesla. In the case of graphene, on the contrary, we're going to be now around 4 Tesla, and it's going to be accurately quantized all the way even to much higher magnetic field. So what this means is that graphene, even in its basic characteristic that is just Landau level formation, has already surpassed some materials such as gallium arsenide, and it's now used as the new quantum Hall resistance standard. But well, that's graphene on CVD graphene on silicon carbide. So this is not a super clean system. If we want to make our device cleaner, we need to go to van der Waals heterostructures. So in van der Waals heterostructures, we can mix materials. For example, like here, you see different types of materials. The materials are going to be held each other by van der Waals forces, which means that we can stack them as we want. We can pull them apart. We can restack them. We can do virtually everything we want. The way we do this, I think Dima already explained, but I'm just going to pass through it quickly, is we take a polymer, we pick up the first layer, with this one pick up the second one, the third one, etc. So this guarantees that the graphene that we have in the middle, it's always clean. It's going to be perfectly clean, okay? And in fact, if you take one of these stacks of 2D materials and you make a cross section, you can see in TEM measurements that there is nothing between the layers, okay? There are only van der Waals forces holding them together. So establishing this method allowed, in fact, to go from a quantum Hall effect of graphene on silicon oxide that was barely visible at high magnetic field, and that it was didn't even show degeneracy liftings, to a system where we can observe already degeneracy liftings for the same magnetic field, and to go even further, one where we can observe the integer quantum Hall effect to very low magnetic fields with a quite complicated structure, I must say. So today the cleanest devices were in fact recently measured in a new technique that is called bleaching, where at low temperatures you are able to bleach the defects in boron nitride and get even cleaner materials. So for example, here you can see that the magnetic field at which you can obtain integer quantum Hall effect is very low. The same happens to the fractional quantum Hall effect, a very low magnetic field, and you can observe electron solids, also a very low magnetic field compared to what it was observed before. Okay, and this is graphene, perfect. So we have the 3 landmarks that I showed you before: integer quantum Hall effect, fractional quantum Hall effect, electron solid states. Okay, but we are interested in moiré materials. Okay, so a moiré material is the one where you see or where you are able to generate a superlattice. These superlattices are going to be the bright spots that you're going to see in this animation. Okay, it's going to depend on the angular alignment between the layers. In this case, I'm using the example of graphene on boron nitride, which has a difference in lattice constant of 1.8%. So the size of this new moiré lattice is going to depend on the difference between the 2 lattice constants, on the lattice constant and the angle between them, which means that just changing the angular alignment between the layer, as you saw in the animation, I'm going to be able to go from something very close to 0 as a moiré superlattice to something very large, around 14 nanometers. But what's the origin of this? This is just an effect of who is near you, in fact. So you can see in these 3 spots that we picked that the Moiré effect is just related to the fact that not every carbon atom is going to have the same environment. However, another carbon atom at a certain distance called lambda is going to have the same environment. This creates a modulation, a periodic modulation of the landscape. Okay? So this has been observed in STM measurements for a long time. So we can see that changing the lattice, the angle, sorry, between the two lattices, we can change the size of this moiré pattern. And very importantly, I'm unfortunately not going to talk about it, but it's something that it's extremely important for experimentalists, theorists, and everyone else, is the fact that you can see that for very large superlattices, here you are not just going to have a moiré pattern, periodic potential that is superimposed, but you are also going to have a strain that is developed inside the moiré lattice. This is because it's more favorable for graphene to stretch and match the lattice of boron nitride instead of just staying in its original position. So this strain is going to develop all around. It's what we call the commensurate state because graphene stretches to commensurate the lattice of boron nitride. And it's the responsible of many features that we see, but that I unfortunately don't have the time to talk today. So let's see in transport what is the meaning of all this. So if I have graphene on boron nitride, as what I started saying, I have a linear energy dispersion, okay? So as in my previous example, what is going to happen if I measure the longitudinal resistance of my graphene flake is going to be, I just have a strong peak in the resistance, okay? Now, if I have a superlattice, if I align graphene and boron nitride, I have a superlattice of size lambda, I'm going to modify the electronic band structure, and this is just band folding. Now I have a periodic potential that is superimposed, so my Brillouin zone is going to be smaller, my bands are going to be folded, and I'm going to have new energy gaps that appear in the system. In particular, the central energy gap, the one of the charge neutrality point, it has two origins. The first one is because I'm breaking inversion symmetry in my system, and the second one is because of the strain that is developed in the commensurate state. So now, if I measure transport there, I'm going to see a new feature. I'm going to see this peak that shows up, okay? Please keep in mind that these are measurements at room temperature, which also means that this modification is strong enough that I can see it even at room temperature, okay? So back in the days, in a long time ago at Columbia, we developed a technique where using an AFM tip, we are able to change continuously this, the orientation between graphene and BN, and you can see that as we change this orientation continuously, this peak moves because the position in energy of the satellite peaks is going to go down and up. This is just the band folding being larger or smaller. But okay, I have a Moiré material. What about topological states? So the first thing that Moiré materials allow us to do with respect to topological states is the observation of the Hofstadter butterfly. I wish I could get into the details of the Hofstadter butterfly, but this is going to be like a 4 hours talk, so I'm not going to go to that. I'm just going to tell you that this is a beautiful representation of what happens in energy to a system where we can put at least one quantum of magnetic flux per unit cell. But now our unit cell is much larger, so maybe we can achieve this new limit. So to simplify this Hofstadter butterfly, we can replot it as the number of charges per superlattice as a function as well of the magnetic flux. And this is just what we call a binary representation. And what it says is that, in fact, the gaps, we can see these gaps just as a linear trajectories in the density field diagram, okay? And this, in fact, these gaps can be represented by the Diophantine equation. This Diophantine equation is going to have the number of particles per Moiré superlattice. It's going to have the flux, and in particular, of particular importance, it's going to have this factor T and this factor S, where T, it's in fact our Chaire number, okay? Of course, in graphene was not the first time that people try to reach this limit of the Hofstadter butterfly. There are measurements that date back to the 90s where they use gallium arsenide heterostructures and they pattern holes on this to try to observe the effects of having a superlattice. In this case, the superlattice is much larger. It's around 80 nanometers. And with the technology that it was available at the time, they managed to see some signatures of the Hofstadter butterfly. However, the disorder was too large, and they couldn't see anything more clear. Okay? But in graphene aligned with boron nitride, we were so lucky that these systems are easy to build that, in fact, 3 groups in the world observe the Hofstadter butterfly at the same time. Okay? So this is just an example of how the Moiré materials were changing the landscape even 10 years ago. I want to give you just a quick look of these states. It's going to be a little bit more clear in a second. But in particular, I want to flash this measurement here because it seems to me insane. It's like you're going to spend the rest of your life just trying to find gaps and trying to analyze and understand what is going on here, although they did a pretty good job. Okay? Now imagine, you can have this with one Moiré superlattice, but you can also use the technique I told you before to make your first Moiré lattice with the bottom BN, aligning the bottom BN, and then just change the alignment with the top BN and now have a second superlattice. Okay? This will allow you to have even larger Moiré supercells, which in terms of what's happening in the Hofstadter butterfly, it makes everything way more complicated. So I'm going to try to keep it simple. I'm not going to go there, but I just wanted to show you that we can even modify further these states to have even larger Moiré superlattices. So to give you a real example of what this Hofstadter butterfly is doing or what it's capable of showing us, we're going to go and talk about a material that is as interesting as graphene, but it has more tuning knobs, which is bilayer graphene. So now we are going to just put another layer of graphene on top of it in what is called a Bernal stack, which means that one layer is shifted with respect to the other one. Our band structure is now going to be parabolic. And more interesting, now we are able to apply a displacement field, so an electric field perpendicular to our sample. And with this, changing its magnitude, we are able to tune a gap in this system. This gap is only going to depend on 2 things. The first one is the interlayer hopping, and the second one is the difference in potential between the 2 layers. So let's put this aside. The way we do this experimentally, the way we tune this displacement field experimentally, is by having 2 gates, by applying 2 voltages to the system, okay? So this is a real measurement. Here you can see that the resistance increases, decreases, and increases as a function of, as I change the 2 gates, which means that I'm opening the energy gap, closing it, and opening again. We can replot this as a function of displacement field and density, and we can see that for 0 density, which is charge neutrality point, we have this energy gap opening and closing. More important than that, which is already quite important, is the fact that with this electric field, we can then change the position of our wave function, okay? What does it mean? It means that when we have a positive displacement field, we're going to be pushing the electrons towards the top layer or the holes towards the bottom layer. And the same is going to happen for a negative displacement field. I'm going to be pushing either the holes towards the up layer or to the bottom layer. And this is going to be very important because then it means that I can put my electrons closer to the Moiré lattice or farther from the Moiré lattice. Okay? So where are we? Bilayer graphene. We have an energy gap, we have a parabolic energy dispersion, which also means that our interactions should be larger. And in fact, they are. When you look at what happens when you apply a magnetic field in the lowest Landau level, you can see that now this lowest Landau level has a combination of orbitals, spins, Landau level index, etc. But you can also see the presence of very prominent and very clear even denominators fractional quantum Hall states. And even if you have a look here, you can see the formation of electron solids, which means that we have recreated already in bilayer the same things as in gallium arsenide. We have integer quantum Hall effect, fractional quantum Hall effect, even denominators, which we didn't have in monolayer graphene. And now we can recreate and play around with the electron solid as well. The other thing that was first time that was possible to do, it was thanks to the qualities of bilayer graphene and its properties, is in fact the observation of an electron solid in the integer quantum Hall effect. So this electron solid is a Wigner crystal, and we are able to observe it because graphene is on a surface. So we can do STM measurements. These are STM measurements performed in the Just Danny group recently. So every time you see a reddish spot, that's an accumulation of charges. And you can see that they are distributed, they are organized. So in fact, they can see as they change the filling factor of these Landau levels, how the lattice constant changes, which means how this becomes larger or smaller, and how they compete, how is the competition between this Wigner crystal and the fractional quantum Hall states. So this is possible only because graphene, it's on the surface. In gallium arsenide, it was not possible to observe Wigner crystallization. It was measured but implicitly understood. So now, Hofstadter butterflies. No, we were at that because this we already saw before. Let's put a moiré on top of that. So if we look at the Hofstadter butterfly of a bilayer graphene, in particular at the very high flux, very high number of flux per Moiré superlattice, which means a high magnetic field, we are going to see just a full zoology of states. And these states separate or have its own topological significance. So what we are seeing here, it's what I think extremely beautiful map of all the topological states that we can have. So each one of these represents a topological state obtained by the Diophantine equation, and they are going to be classified depending on the values of t and the values of s. So remember that the values of t are the equivalent of the Chaire number. So we are going to have integer Chaire number, which is the integer quantum Hall effect, fractional Chaire numbers that are here, that are the fractional quantum Hall effect. Then we have integer s and t, which are Chaire insulators. These are the replicas that you saw before in the Bannier map, which are the black lines here, which means that these are replicas of the main Landau fan that occur at different filling of the Moiré superlattice. You're going to also have two things that are new and very exciting, which are fractional S and T, which is a fractional Chaire insulator. We're going to see it just in a second. And we're going to have symmetry broken Chaire insulators. Both of them are the result of interactions, and they are very active subjects of research currently. Okay, so why can we see this here and not in a regular bilayer graphene with on BN but not aligned? The reason for this is that you need a ratio between, you need certain number of interactions, but also you need to compete, in this case, with the lattice potential. And in fact, this fractional Chaire insulator can be stabilized only in a range of this ratio. After that, what you get is a compressible state, which is just a solid, an electron solid state. So if you think about it, all these fractional Chern's insulators, integer quantum Hall effect, and all these, the origin of them is just Landau levels, flat bands, okay? So now the question is whether can we make flat bands without magnetic field? Are we able to do this? And since 2018, we know that we are able to do this. So in fact, when we take 2 layers of graphene and change the angular alignment, as we can see it in this numerical simulation, the electronic band structure is going to get modified, and at a certain angle called the magic angle, what we're going to have is a flat band, okay? This flat band is the responsible, or it's believed to be the responsible of the observation of strongly correlated states, superconductivity, etc., in twisted bilayer graphene. And what is interesting here is that the fact that you have a flat band will quench your kinetic energy, and now your interactions are going to become much prominent, okay? And that's why you get all these states. Of course, this was once again the first measurement, but not long after, a lot of new superconducting domes, correlated states, etc., were observed in the same system. However, there is a problem with twisted bilayer graphene. The main problem with twisted bilayer graphene is that you can have a beautiful zoology of states to study, but you try to replicate exactly the same angle with exactly the same characteristics, and you might find something that is different. And this is related mostly to angle disorder, strain, this commensurate state that I told you before is also playing a very important role, the relaxation of the atoms. But then, this is also a very active research topic at the moment, how is that we can have the same angle but different physics? What are the other parameters that are playing an important role here? So, okay, this is very interesting, but we are mostly concerned about topological states, and this is not, at least not that I know of, a topological state. However, if we take exactly the same system, so twisted bilayer graphene aligned at the magic angle, and we also align the boronitride that is as a substrate, we are going to observe quantum anomalous Hall effect. So why is this important? Remember that I just showed you, you can have 2 moirés and they might interfere with each other, they might lift new symmetries of the system. This is what's happening here. You have 1 moiré that is created by the twisted bilayer graphene, and a second moiré that is superimposed that is created by the graphene and the boronitride, okay? So let's see those results of quantum anomalous Hall effect. So when we measure the resistance as a function of the density in a quantum anomalous Hall state, what you're going to see is that for zero magnetic field, you're going to have a strong increase of your Hall resistance, and this value here is going to be quantized. At the same time, you're going to see a decrease in the longitudinal resistance. So exactly the same as the quantum Hall effect, but this time without any magnetic field, okay? So, in fact, if you go and change the magnetic field, you place yourself, you're going to place your Fermi energy at this position, so your gate voltage, and you're going to sweep the magnetic field back and forth. You're going to see these hysteresis loops. So these hysteresis loops tells you that there is a magnetization, an intrinsic magnetization of the system that is switching as you change the magnetic field. Okay? So the reason why we believe we observe this quantum anomalous Hall state, which, by the way, has only been observed in 1 sample in the world since 2020, okay, is because when we have twisted bilayer graphene, we're going to have these topological bands but you can see that the total Chaire number is equal to 0, so we don't see any topological effects. Adding the boronitride and breaking an extra symmetry with the boronitride is going to lift one of these degeneracies, and now your Chaire number is going to change. And that's what makes possible the observation of this integer quantum Hall effect without magnetic field or anomalous quantum Hall effect. Of course, since this has been observed in just one sample in the world, there are a lot of questions about it. What is this origin? How is the BN really playing a role? What is the temperature, angle, and current dependence of all these? Can it be metrologically quantized? Because it's going to be a revolution if for metrologic measurements we can do the same kind of measurements as in the quantum Hall effect, but without magnetic field. Okay? So this is very beautiful, and is one of the most remarkable results on twisted bilayer graphing to my own personal taste. However, at that moment, then people started to think about, can we make this, can we make flat bands and these kind of systems to observe these phenomena in other materials, okay? So I already told you about monolayer graphing and bilayer graphing. So monolayer, you have just one of these. Bilayer, you have the second layer that is stacked. Now you can add a third layer, a fourth layer, fifth layer. And what is interesting here is that you can see that the energy dispersion goes roughly, without, it's just a first approximation, roughly as the power law of the number of layers, which means that every time you add a layer, you're going to have an even flatter band near charge neutrality point, okay? So now you can imagine, if I add a Moiré potential to all this, then I'm going to cut my bands, I'm going to make the same thing I did before, this band folding, and I'm going to isolate my flat band. So is this possible or not? That's a very good question. Is this what is happening or not? That's an excellent question. And the main problem to see all the results of rhombohedral graphing, by the way, sorry, I completely forgot. This organization of layers is called rhombohedral. There is another one which is more stable called Bernal, in which this layer is going to replicate this first layer. And in that case, you are not going to have the same bands. The band structure is completely different, and it's topologically trivial. Okay? So, but let's focalize now in Moiré superlattices in rhombohedral graphing. So whether this really isolates the bands and it's good for observing topological states, it's still under debate in the sense that when we have the exactly same kind of system and we measure their transport response, we do observe topological behaviors that I'm going to show you in a second. But contrary to what you will expect, we observe this topological behavior here in the Moiré distant regime. Okay? So remember, I told you before, if you apply a displacement field, you can push your wave function either closer to the Moiré or farther from the Moiré. In the case of rhombohedral graphing, in fact, you can observe topological states of integer and fractional anomalous quantum Hall effect, but this time is when we are far away from the Moiré, okay? Which is a little bit counterintuitive if I think that, well, if the Moiré is doing what I think it's doing, I should see it in the other side. But okay, so what is also very interesting So the other thing that is important to keep in mind, that this is a Moiré distant, but it's not pushing the wave function to a place where there is no Moiré, because remember this commensurate state I told you before, this will propagate to a certain number of layers. We don't know how far it's going to propagate, but we know that at least to 10 layers, we can still see the moiré, the commensurate state. So it's just a moiré distant, but not a moiré less part of the diagram, okay? So now to explain this, we can perform some numerical simulations of the system, and we can find that we are going to have, in fact, a flat band, a non-trivial flat band with a bunch of trivial bands around, as Antoine said before. So this flat band might be the responsible of observing this integer quantum Hall, anomalous quantum Hall state. However, it's not necessarily the reason why we observe the fractional Hall effect. So just to give you a little bit more of a hindsight of these states, so remember that before I told you if you sweep the magnetic field, you can switch the magnetization, the spontaneous magnetization of the system, and now you're going to see that this is quantized to fractions of the E squared over H. Okay? So what is very important to keep in mind when you look at these loops, hysteresis loops, is that remember twisted bilayer before? It was not that clean. It had a bunch of jumps in the middle. And the reason for that is because you have angle disorder in twisted bilayer graphing. You have a lot of different angles in the same sample, which are going to give you different effective magnetizations. However, rhombohedral graphene seems to be an extremely clean material, where we have a moiré superlattice, which, as it is formed with boronitride and not with another graphene, it's way more stable. And that's why you can see this hysteresis loop being very, very clean. So, okay, we have recreated integer quantum Hall effect without magnetic field, fractional quantum Hall effect without magnetic field. Maybe there are other surprises to come. And in fact, just to give you an overview, so now we're going to have to change the number of layers. We're going to go from pentalayer that we were working before to 4 layers. So by the way, these effects, topological effects, has been observed in 4, 5, 6, and 7 layers. Superconductivity has been observed in 3, 4, 5 layers only. Unless someone published a paper this morning that I'm not aware of, but I'm going to try to read it when I go back home. So what I want to say here is that for rhombohedral 4 layers graphing, you can still see a full zoology of topological states. Now you have topological states with different Chaire numbers, fractions, integers, etc. But you can also see superconductivity pockets, okay, in exactly the same system. So this here, it's what I truly consider to be the most beautiful curve I have ever seen, and I have seen before a lot of curves, where you can see superconductivity and quantum anomalous Hall effect in the same device, in the same, at the same moment, just by changing the concentration of carriers of the material. Why is this so beautiful? Because if you ignore the Hall resistance, you're going to see that both phenomena have the same behavior, no? A longitudinal resistance going to 0. But these are completely different phenomena. So these are not related in this case. I mean, they are related, but not in the same, in the way we believe. So now, this is the first observation of both superconductivity and a topological state in the same device, which can bring us to the development, maybe in a few years, of new states, such as topological superconductivity, using quantum Hall effect to connect superconducting qubits, you name it. We have almost everything. So, okay, it seems that it is maybe even more interesting than all the topological states we saw with magnetic field before. We can have, because we can have also superconductivity. Now, the other thing that you haven't seen yet is the electron solid, no? At the beginning, we were talking about we have integer quantum Hall effect, fractional quantum Hall effect. Keep increasing your interactions, you're going to have an electron solid. Well, it turns out that you can also have an electron solid without magnetic field. So nowadays, with these incredibly clean samples, you can see the reentrance of the integer quantum Hall effect at very low temperatures, but without any magnetic field. This means that the interactions become higher and higher, and then your system is going to organize as it did before. Whether this is a bubble or a striped phase is still under debate, but there are very recent developments by the GIA group, by the Lee group in Texas that show that this might be a bubble phase. So, does Moiré matter? What do you think? Is it important for this topological state? Is it really important? Turns out that it might not be the only way, okay? So this example that I'm going to show you, it's a pentalayer rhombohedral graphene, although I think there is a, no, yeah, it's good, in a close proximity with tungsten diselenide, a material with high spin-orbit coupling, okay? So in fact, if you put these two in contact and make exactly the same measurements as you did before, you're going to observe in this little pocket anomalous quantum Hall effect, which is as clean as before. The difference is that the Chaire number is higher now, but it's still a Chaire number, it's still quantized, it's still the same physics. So, truth to be told, Moiré might be important for Moiré materials, but Moiré is not the only way, and it's not a necessary condition to observe anomalous quantum Hall effect in rhombohedral graphene. So with that, I would like to summarize. First thing is we did it. We passed from this $1 million machine to tape, so great. We can unlock with these Moiré systems new limits of physics that we have been doing all these years. We can have extremely rich new physics with these Moiré systems that go from replicating the original topological states, integer, fractional, and electron solid states in graphene, to making also the same integer, fraction, and electron solid states in rhombohedral graphene without any magnetic field. So with that, I would like to thank you for your attention.